Hi, everybody. Welcome to the Toronto Geometry Colloquium. This is a weekly web series about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities.
Every week, we'll have an opener talking about their cutting-edge research, followed by a headliner giving us a keynote presentation.
And this week, we have two very exciting talks. Our opener, Yun-Chun Chen, is going to talk about a neural shape matching self-supervised object assembly with adversarial shape priors. And our headliner, Professor Anandkumar, will talk about roles of graphs and tensors in deep learning. So first, it is my great pleasure to introduce our opener, Yun-Chun. He's a PhD student from our home university, advised by Professor Animashree and Alex Jacobson. And he is a very talented PhD student who already have an impressive amount of top-tier publications at his second year. His research also spanned a wide range of areas from fundamental vision problems such as domain adaptation to train robots to do some low-level manipulations. And recently, I'm even more excited to see that Yun-Chun's stepped his foot in geometry processing. And I'm very excited to see how his expertise could bring us new insights in some traditional geometric problems. And today we are very lucky to take a glance at Yun-Chun's recent CBR paper about how to connect pieces of shapes together. Please take it away.
Thanks, Derek, for the introduction. Okay, so let me share my screen. So today I'll be talking about neural shape mating. This is a project that has been accepted as CVPR and will be presented at New Orleans this June. And this is a joint work with Halda, Dylan, Alec, and Animashree. So to motivate this problem, we can see that in many real-life examples, what we want to do is to connect objects together, like putting a plug into a socket or putting a pen, joining a pen in the cap. Those are examples of shape assembly. But shape assembly can have different forms and different settings. For example, for this kind of cases, when we are doing shape assembly, each part does not have a well-defined semantic meanings. But when we join them together back to the original shape, it has a global shape meaning. So we want to look at this sort of like geometric shape assembly where each part doesn't have a semantic meaning, but when we join them back together, there's a well-defined shape for that object. So to take a first step, we want to look at a problem where we only consider two parts. So we name this task as a pairwise 3D geometric shape assembly task. And the input of this task is we're given two shapes. So for example, on the first column, we're given a fractured shape pairs. And to make this setting more realistic, we will convert them into point clouds. And this will become the input, and we will design a model that takes as input a pair of point clouds and try to predict poses so that when we apply the poses to transform the meshes or the input point clouds, we are able to obtain the assembly result. So the high-level goal is to disassemble an algorithm that learns to assemble the two pieces together. And the application of this task ranges from furniture assembly to toy assembly, or even to object kitting. So it has applications in vision, in graphics, or even in robotics. Those applications requires reasoning about the fit between object pairs or between different parts to do some meaningful object-to-object or part-to-part joining. So to take a step further, we first formulate this task. And we are given 2 point clouds denoted as PA and PB, as shown on the first column. And then we want to design a model which is denoted as a block here. We can treat this one as the black box for now. And then what we want to do is to predict a rotation and translation for each input point cloud, so that after prediction, when we apply the predicted poses to transform the input point clouds, and then we take the union of the two transformed point clouds, this will become the assembly result as shown on the right-hand side. So we can formulate this task as a pose prediction problem. Instead of predicting an independent pose, we are predicting a paired pose for a pair of parts. So let's look at our method first. So given two parts, we do some standard feature extraction as in existing point cloud processing papers. So we will have a dedicated encoder here. This one can be realized by using state-of-the-art point cloud encoder, such as PointNet, PointNet++, or even DGCNN and their follow-up methods. And in this work, we use DGCNN due to its superior performance compared to PointNet and PointNet++. So we can encode point features denoted as FA and FB. And since we're doing post-prediction, and the post-prediction has to depend on the other shape, we cannot just independently predict a post without seeing the other part. So we develop a module that can reason about cross-shape correlation. And to achieve this, there are several variants we can do. For example, we can compute feature-wise correlation, or we can have a learnable model, either using a transformer network or other sort of graph neural networks, for example. And here we choose transformer networks that will take as input two sets of point features, compute pairwise similarity scores, and do some sort of reasoning, and it will predict hidden features HA and HB. So the feature highlighted in the yellow color will contain information not only for the input point cloud, but also the information of the other point cloud. And then we will do some feature aggregation by doing a max pooling on the feature FA, so that we can aggregate them into a capital FA feature here. Similarly, we can do the same trick for feature H to get the capital H feature. And then we will concatenate them together and pass it through a regression network that will predict a quaternion, which can further be converted into a rotation R and a translation vector. And if we have ground truths for the poles, then we can do a supervised training regression loss here. And the regression loss can be formulated right here. So we penalize the difference between ground truths and the prediction by using this equation. So we can do this for point cloud A and also for point cloud B. But doing this alone is not sufficient, because we still only, we didn't know whether the assembled result will look visually realistic. And what if there are multiple solutions exist? For example, when we are joining two shapes together, what if there is some symmetry there that might lead to some confusion or ambiguity? So what we do here is we want to learn some sort of global shape prior. And to do so, we cast this one as an adversarial learning problem, where we have a discriminator that tries to tell whether the input point cloud is from ground truth or from a predicted assembly. So the discriminator will be trained in an adversarial learning manner, and this discriminator will allow the model to learn how to assemble them into a visually realistic object. And the next thing we want to address is for a given shape, we can describe it by many different kinds of point clouds due to point cloud sampling randomness. On the other hand, real-world point clouds may contain measurement error or noise. So to account for these two shortcomings, we want to do some sort of shape reconstruction so that the learned feature will be more robust to the point cloud randomness. So we use existing methods such as SDF here. So that at the same time, we want to reconstruct the feature and attach with an R3 coordinate and predict the SDF value. And training this network using an SDF regression loss will allow us to learn implicit shape reconstruction so that the feature F here will be more robust to input point cloud noise. And we talk about the method. The next thing is, how do we get this kind of data? So we generate, we develop a self-supervised data collection method where we collect a bunch of object meshes that are watertight. And then for each object mesh, we will randomly cut it into two pieces. And the way we cut it is by constructing a height field. And the height field can be parameterized by different parametric functions. So that having this kind of definition, we can create different types of cuts. And after cutting, we can apply random transformations to each part. So we can generate this kind of paired example. And for each instance, we create two different versions. The first one is the shell option, where we first shrink the object mesh so that we can create a thin shell, then do the cutting. The second one is doing the solid shape is by directly applying the height field to intersect with the object mesh. And these will become the data that we use to train our network. And so the entire process, there's no human in the loop, and it's fully self-supervised. The network will learn from this data. So if we compare our results with state-of-the-art methods such as GN assembly on the fourth column of these two figures, on the right-hand side, on the left-hand side, that is an error by computing the mean square error between the predicted rotation and the ground truth rotation. And translation error is shown on the right-hand side. So the lower, the better. So you can see that our method significantly improves over existing methods. And qualitatively, if we're given this pair of input point clouds and the ground truth is shown here, we can see that existing methods, their predictions are completely off. Even if using state-of-the-art methods, they still cannot predict plausible results. Our method predicts accurate poses so that they can be assembled together pretty well. And the future work of this one is to go beyond from two parts to multi-part. And there's a follow-up work that is a joint work with Sylvia. And we created a large-scale data set by fractured an object into multiple pieces. And I think this is an exciting problem and has some applications in biology and further maybe some archaeology examples. And I think that this concludes my presentation. Thank you.
Thank you, Yun-Chun, for this fantastic talk. So as usual, we will proceed to the talk about headliner and have a joint Q&A near the end. So now it's my time to introduce our headliner, Professor Anandkumar. So she's another speaker in our colloquium who really does not need an introduction, but we still have a short summary for her amazing achievement. So she's currently a brand professor at Caltech and also a director of machine learning research at NVIDIA. And her research covers a wide range of topics in general numerical methods and machine learning, just to name a few, such as the famous born-again neural networks and also the very intriguing sign SGD algorithm, which only consider the sign of the gradient in the optimization. And her achievement definitely comes with an article length of awards such as like Sloan Fellowship or the NSF Career Award. And we can definitely go on and on and on for the rest of the colloquium about her achievement. But personally, I can't wait to hear more about Professor Anandkumar's talk. So without further ado, please join me to have a big welcome to Professor Anandkumar.
Thank you. Thank you for the kind words. And yeah, thank you for the invitation and a really great opening talk. So let me share my screen. Let me see here. Hope everyone can see that. Yeah, so I want to give you a broad overview of the importance of incorporating geometry into deep learning methods. And geometry can come in different forms. Perhaps graph is the most natural one. You think about how we can incorporate graph structures into our learning algorithms and what kind of applications is that really important. Tensors are indeed at the core of deep learning, right? So we represent our data as multidimensional arrays. But I want to take that a step further and ask, not just representing them as arrays, can we go from linear algebra operations such as matrix multiplication to tensor algebra operations such as tensor contractions? You can think of it as multiplying across many different dimensions of tensors and decomposing them in various ways. And that extension pays off very well in a number of applications, both in deep learning as well as in quantum many-body systems. And also I'll talk about spectral methods. If we think about a change of basis, like the spectrum is an alternative basis where in many cases it becomes much easier to process signals. I mean, this is the foundation of signal processing, and Fourier Transform is one of the basic transforms, right? Can you look at the frequency content of the signal and process in the frequency domain instead? And where is the connection between these classical signal processing methods and the modern deep learning methods? And we will see that bringing those together has had a huge impact in learning partial differential equations and other multi-scale phenomena. So yeah, very excited to tell you about a number of these developments today. So indeed, as I mentioned, my focus will be to show you various applications of graphs. And as you can imagine, especially molecules, right, are represented through bonds between atoms. So it's natural to incorporate the graph. But is the Greek graph all you need, or do you have additional information? Here I'm showing you blobs, right? And you can think of these blobs as a form of how much dependency there is between the atoms. So, some atoms could have outsized dependency that is long range, and the others could have much shorter dependency. In this example here, there is the main benzene ring, and then there is the side chain, right? And you can see the blobs on the side chain are smaller compared to the one in the ring because, there is much stronger forces in the main ring. So it is a combination of the graph structure, but also other information of how the interactions happen on this graph. Tensors, as I mentioned, are multi-dimensional objects, and this occurs as we go to multimodal data, higher dimensional data. The previous talk had point cloud, right? So that is 3-dimensional. And if you add time, 4-dimensional. And if you add both point cloud as well as image data, this would be even higher dimensional. So how do we process these higher dimensional data instead of just reducing them to matrices is, I think, a very interesting and an important notion. And the last one, as I mentioned, is how we can think about signals in the frequency domain, as we are decomposing them into sinusoids or other basis functions. Is there a better representation? And so instead of learning the entire representation from scratch, which is what standard neural networks do, is there a way to incorporate this inductive bias and do more processing in the frequency domain? And what would be the kinds of neural network architectures that can do this effectively? And so we'll explore these aspects here in this talk. And this is very important in so many scientific applications. I already mentioned molecules. If you think about fluid dynamics, materials, they have structures incorporated in them, especially multi-scale nature. And that's where looking at them in the frequency domain gives you many more insights. And in fact, some of the numerical methods are also pseudospectral methods that do processing in the frequency domain. So deriving that inspiration, I think, is really critical. And with tensors, especially higher dimensional partial differential equations, or such as quantum many-body systems, we need ways to incorporate these high dimensions in a way to express their entanglement or correlations in tractable ways. And tensor networks, right, which are essentially tensors that are decomposed in certain low rank forms, are very crucial there. So, and I do believe this is a great time to be working in AI for science, a very exciting time, because we've seen the surge of data in scientific domains, and we can use our state-of-the-art large models. We've seen the benefits of this expressivity in language domain. Can we do this into other domains? We've seen benefits in multimodal models, right, vision models, but can we do that on scientific data? And what are new challenges and requirements that go beyond standard computer vision or language? And that's, I think, something that is still very much a green field, but so many opportunities lie ahead. And the other important aspect to think about when comparing machine learning methods versus the traditional numerical methods in these scientific domains is with the use of machine learning, you have now the ability to do it in much lower precision, right? So we continuously keep reducing the precision of our computation. The latest Hopper architecture by NVIDIA will have FP8 computation, right? And in fact, we have a paper where we show you can even throw away the mantissa and only keep the exponent bits. And by changing the training algorithm, you can train directly in these systems. So we are pushing all the time the boundaries of precision of what's needed for machine learning. But that's not the case with numerical methods. Like fluid dynamics, you have these very fine scale phenomena that affects the entire outcome. You get that wrong and everything just goes off. And that requires very high precision, FP64, or even higher sometimes. And that is such a delicate and an unstable aspect that is very hard to tune, and you need this high precision. And so the hardware will go a much longer way with machine learning. And I think that's the proposal for using machine learning in scientific computing, because it combines the benefits of accelerated computing, such as GPUs, right? So if you just look at the improvement of CPU performance that has essentially plateaued, the Moore's law is dead. We need to move to GPUs. But that's not enough by itself, right? We need to further scale this up on supercomputers. We are building bigger and bigger supercomputers. We are now in the exascale regime, but that's still not enough. We need the power of machine learning to do so many of these challenging applications. I'll talk about two cases quickly. For instance, if you want to model climate change accurately, over the next several decades, right, we have to reduce the biggest source of uncertainty, which are the low-lying clouds called the stratocumulus clouds. And this is very complex to model the turbulence and movements in these clouds. And it is estimated that you would require about 100 billion times more computing than what we have today, even if you took all the world's supercomputers. And so this is so enormous that we cannot just brute force our way into this problem. Same with drug discovery, right? So we want to understand properties of molecules and materials. The fundamental equation governing that is Schrodinger's equation, right? There's no mystery. I mean, this is the equation. If you can compute it, you've solved all of chemistry. But the problem is to compute that brute force, even for a molecule of about 100 electrons, it requires longer than the age of the universe on the current supercomputers. So these problems are so out of reach from current computing capabilities that what we are asking is, can machine learning make a big material difference? Can we really push the envelope with the use of machine learning? And you'll see some examples of this. This was last year in a large interdisciplinary team coming together to understand the coronavirus and how it interacts with the respiratory aerosol. And it's a multi-scale experiment. So this is a billion atom experiment we did. And so there you see our friend, the virus, and you see in light blue, those are, and these are the part of the spike, right? And understanding that spike mechanism is where a lot of the interaction happens with the rest of the environment. And what you see in yellow here are the calcium ions in the respiratory aerosol. And how this calcium ion binds with parts of the spike protein is really important to characterize, because that tells you how infectious it is, how it's going to interact with the lung tissue. And so this is something we could do effectively by going all the way to quantum level predictions, but with the use of machine learning. So for the first time, we could compute this over thousands of atoms with traditional methods, what is known as density functional theory. This is impossible, right? And AI for the first time has enabled such computation. And with such methods, you can very quickly do other optimizations, such as optimizing the geometry of the molecule, like predicting what the geometry should look like, right? So based on minimizing the energy, these aspects are really out of reach with the traditional methods. And so we have here thousands of times speed up compared to traditional methods that makes this possible. We're also seeing this in many other domains. Here we have weather prediction. So we trained our model, we took all the historical weather data, and we trained our model in completely data-driven manner, right? So far, we didn't incorporate any physics. And we wanted to see how well it does compared to standard numerical weather prediction models. The one in white you will see here is the numerical model. And what you see is that our model is capturing many of these wind patterns very effectively, including this hurricane. You see that it's able to track the trajectory pretty well, and sometimes even better than the numerical weather models. And this is one aspect that is the power of data-driven methods, that there are lots of modeling errors with numerical models, because you're making all kinds of physics assumptions that are not true. And we can overcome that with the use of data-driven models. And so at the same time, this is about 100,000 times faster than the current numerical weather model. So you can also run large ensembles and have a big reduction in uncertainty, and which is very important for extreme weather prediction. Climate change, is happening, right? So, and there is a big push to reduce emissions. But even in the best case scenario, even if we stopped all emissions, we are already past the point. So we need to actually have negative emissions, meaning find ways to capture carbon dioxide back from the atmosphere. And so these kind of strategies of how to do climate change mitigation. One such strategy is to capture carbon dioxide and store that deep underground, and see how we can model the pressure buildup in these reservoirs. There's interaction between water and carbon dioxide, and and we have to kind of look into the shape of the channels and so on. And this is important because it's a safety requirement, right? How would the pressure build up, especially over several decades, if you're pumping and storing this carbon dioxide? And so these tools help modeling this much faster. So it'll help companies that want to do carbon capture much more effective modeling. So I want to quickly show you some of the techniques that went into these outcomes, right? So you saw some really exciting developments. So what are the fundamentals? How did we get to this point? So the first work I want to present is called the neural operator. This is thanks to the interdisciplinary team at Caltech, where we began this work. And indeed, we can think of partial differential equations or other multi-scale phenomena such as weather forecasting, right? So how do we solve these kind of hard scientific simulations? And so if you think about partial differential equations, the approach we want to take is a data-driven one. It's a learning approach. And the idea is if we can learn a mapping between how the initial and boundary conditions, right? So some initial conditions map to the solution or the output, then we can predict it for any new instance. So this is different from a solver that only solves one instance of the equation through various means. Could be a traditional method doing stepping, right? So the iterative time stepping, or it could be a physics-informed neural network where you're trying to enforce the equation and find the solution. To me, that is still not learning because you're just solving that one instance. You're not learning the underlying operator. So why is this an operator and what does that mean? So why can't we use a standard neural network? Why can't we use a convolutional neural network, for instance? The reason is all these networks are built keeping in mind a fixed sized input and output, right? So we train on images on one resolution, And we also test on images on the same resolution. But in scientific applications, that's not the requirement. We need to be able to query at any point in the domain. We may change our grid entirely. And in fact, the underlying phenomena is very fine scale, right? So if you overfit to only a few coarse grid points, you're not capturing this fine scale phenomena. And that's exactly the challenge with numerical methods, that you need to go to very fine scale. So if we also force our neural networks to go to extremely fine scale, then we are not getting much of a speed up, right? So the question is, can we have it learn on coarser grids, but still capture the underlying fine scale phenomena? And that means this has to be a resolution-free method, a grid-free method. It should be able to generalize from one resolution to another in a zero-shot manner without any retraining. And that is a hard requirement. So how do we get to that requirement? So the main aspect we went about thinking is we need, from the foundations, change our thinking, right? So we want to think about having now, instead of a linear function such as multiplication or convolution, right? So familiar operations in neural networks, we want to be having a linear operator here that can work in any resolution. So essentially, it's learning the underlying continuous, operator in the underlying domain. So one example of that is integration. And in fact, if you had a linear partial differential equation like heat diffusion, right, the solution is given by such an integral operator. And in those cases, in some examples like this heat diffusion, we in fact even analytically know what the kernel is. But in general, you don't know this, and in general, it's nonlinear, right? But the idea is, if we compose such operations with nonlinearity, we get overall an expressive network. So that's the principle. But now the question is, what is a practical architecture that would solve this in a resolution-independent manner? So this is where we turn to Fourier Transform, all the wealth of knowledge in the spectral methods, where convolution becomes multiplication. So what this ends up doing is learning the weights in the frequency domain, and we filter and keep only low frequency weights, do the inverse Fourier transform. And but we come back to the input domain and have nonlinear transformations and do this again. So think of this as alternating between processing in the frequency domain and the spatial domain. So we keep back and forth. And so that means with this alternating processing, we're able to capture both the multi-scale phenomena, right? The nonlinearity means we are able to capture different parts of the spectrum, even though we are filtering out to only low frequency components here. But at the same time, going back to the spatial domain means we can do effective local nonlinearities and change our signal in an efficient manner. And so I think very simple architecture, right? So you just have a few lines of code. It's also very efficient because fast Fourier transform is n log n. So you have all these benefits that it's a simple, intuitive architecture, but also gives you the benefit that this can capture any nonlinear multi-scale phenomena. And it is also resolution independent. You can run this now at different resolutions. And we in fact see this train using only low resolution data, and we directly evaluate the inputs that are higher resolution, right? So these higher resolution inputs were never seen during training. And still we see that it has benefits. It's able to extrapolate very effectively. And we see that in the frequency spectrum as well. It's able to extrapolate much better than networks like UNet. And so, yeah, that's what went into these weather prediction models, multi-phase flow systems for carbon dioxide storage. And we got big speed ups compared to what traditional methods can do. In addition, there is aspects like capturing the molecular dynamics as the coronavirus replicates, and being able to understand as the replication happens, the conformational changes and seeing how we can capture that effectively. Or stress in materials, or lithography, like being able to do very fine resolution simulations. So there's in fact a nice connection between transformers and neural operators. So you can think of transformers as special cases of neural operators. And in transformers, we have spatial mixing, right? So you take patches and then you learn to mix them together. But the self-attention layer is quadratic and expensive. And instead, what we said was we can replace that self-attention layer with essentially these Fourier neural operator layers. So we can learn the mixing in the frequency domain. And we can also do some efficient weight sharing and dynamic updating there. And by doing that, we have now a version of this Fourier neural operator with transformers that is expressive, that is scalable. In fact, our latest implementation, we use this to do weather forecasting that I showed you before, and we can scale this up to thousands of GPUs and also have model parallel versions. So we are bringing together the benefits of these multiple different models and being able to effectively capture this fine scale phenomena. And all this is built into NVIDIA Modulus. It's an open source framework, both TensorFlow and PyTorch. And so you can just give your partial differential equations if you have, and it'll directly convert it into derivatives and give you the answers. Or if it's purely data driven, like the Fourier neural operator, you can also use it there as well. And it has good hardware efficiency. So I want to give you now a few more insights into what went into molecular modeling that I showed you earlier. And indeed, this is a big, part of a big pipeline for drug discovery, right? And molecular modeling is useful in so many different parts of it. But as I said, the question is, how do we represent molecules? SMILES is a popular one. It's just one-dimensional, right? It's like any other language. But it's really not just this one-dimensional structure, right? And the two-dimensional is a better one. It has more information. But really, if you go to the quantum level, it's not just three-dimensional. It also has these what we call orbital interactions. So what are the interactions of the wave functions? So that is, kind of both the graph structure as well as ultimately these wave functions, right? And how they interact between different atoms. And so capturing those kind of features, this is a domain knowledge. And then on top of it, we can do graph neural network, in fact, graph transformers. And we can also build equivariants. So we propose these equivariant neural networks that can take in these orbital features, which are tensors, and we keep equivariance throughout the network. So if the molecule rotates, the output prediction of the dipole moment should also predict. And with this, we're able to get much better accuracies, right, than the standard methods, while being about 2 to 3 orders of magnitude faster. And that's, I think, the aspect that we are faster. And we also require less training data compared to other machine learning methods because they don't incorporate the domain knowledge as well, because they're not incorporating these orbital information. And with this, we can do, as I mentioned earlier, the geometry prediction and so many other chemical properties. And this one I showed you. Yeah, in the last part, I want to give you an overview of what we can do with tensors, which is now taking matrices to higher dimensions. As with any complex mathematical concept, it's always nice to lighten it up with some dogs. But I hope you all see how tensors are generalizations of, from scalars, vectors, matrices to now higher dimensions. And as I mentioned earlier, all kinds of multidimensional data, right, or having multidimensional structures, it's best captured with tensors. And so the idea is, right, historically, people were thinking about first just manipulating scalars. Then came matrices and all the linear algebra, right? The LEPAC, including, of course, the Turing Award this year to Jack Dongarra. So those are all, right, the benefits of parallelized linear algebra. And indeed, how to kind of continue to have block structures and make them efficient has been really at the foundations of GPU and other accelerated programming. But what we want to argue is if we go beyond to even incorporating tensors and tensor contractions, which generalize matrix multiplication to more dimensions, you get all kinds of benefits. So we have a suite of different neural network architectures where you replace a matrix operation with tensor operations. So think of like a linear layer, right? So you're just doing matrix multiplication. But if you now made the weights into tensors, higher dimensional tensor contractions, you're incorporating more structure into that. And so we've seen benefits in terms of compression, because you can incorporate all kinds of low rank structures as tensors, which are much more flexible compared to matrix low rank. The matrix low rank is extremely limiting. People have tried to put low rank matrices into neural network architectures and they just don't work well, right? The degradation is severe, but not with tensors. And we also see really good speed ups because you can do block computations with tensors even more efficiently. There's better parallelism and also better generalization because incorporating this inductive bias. And we are being robust because of this better inductive bias. So this is one of the recent projects we did where, topic modeling at scale. So this was the Me Too movement. So this was enormous amounts of data from Twitter feeds. And we can see all kinds of topics that are extracted in an unsupervised learning manner. So in this case, we used the notion of topic modeling, the latent Dirichlet allocation, and the tensor methods at scale to learn the parameters of these models in an unsupervised manner. And I think for very large scale processing, right, these latent Dirichlet allocation are still the workhorse of topic modeling. And we can scale that up very effectively. The other use case is quantum computing and being able to simulate these quantum systems effectively on classical computers. And to do that, tensor networks have been an important foundation, because if you just looked at all-to-all correlations in a quantum system, this is extremely expensive, right? It's exponential, and we can't simulate that very well. And so people try to do more local entanglements, and those kind of tensor networks are effective to scale, and we still get an insight into how effectively can it solve many problems, such as in this case, max cut problem. And we see here that it's able to, we had some record runs in terms of, sorry, the numbers have kind of gone off here, in terms of being able to efficiently scale this up on GPUs with the use of tensor networks, as well as other efficient encoding schemes that we developed. And so these are all open source. I encourage you to go check out Tensorly, but there is both the standard Tensorly for any operation. So you can run this with multiple different backends, including PyTorch and JAX. So you can use different backends and easily define these tensor operations. And with Tensorly Torch, we made it further efficient because you can just directly define a layer, right, that has tensor operations. So you can just kind of train it end to end as any neural network and define it. And we branched this off and added like all kinds of quantum operations that make it very efficient to write programs quickly and scale them up on GPUs. So yeah, so I think there is a lot of exciting aspects, in terms of AI for science, and I showed you how the benefits of using graphs, tensors, and spectral methods can take us a long way.
Thank you, Anima, for this really inspiring talk on a lot of seeing a lot of impressive results on using AI for those computation. And so right now we will start our Q&A session, but due to some kinds of time constraint, we'll start with a question for Anima, and then we will move on to the question from Yun-Chun later. So we have actually a few quick questions for you. So the first is that at the very beginning, you show a very promising future of using AI for accelerated computing. But however, there are also other research in AI which shows some, for example, some vulnerability of some AI model against, for example, something like adversarial examples. So we wonder, whether, in your opinion, how can we cope with this robustness issue or some generalization issue in the future for AI accelerated computing?
Sorry, there was a problem with my speakers. I couldn't hear the last part.
Okay. So we're just curious because there are also some other research in machine learning shows some.
There is still some. Let me see. Sorry, can you?
Yeah, is it better now?
There is. Let me have to do this. Sorry, because this is. I have a problem with the connector. Give me a second here.
No problem.
Sorry about this. Yeah, go ahead now.
Is it better now?
Yes.
Okay. We're just curious because there are also other research in AI which shows some state-of-the-art machine learning models may suffer from robustness issues, something like adversarial examples. But so we are wondering, in your opinion, how can we cope with this robustness issue or generalization issues for those future AI accelerated computing?
Yeah, I think robustness is a really important part, and indeed, right? So there's a lot of brittleness in current machine learning models, but there's also a lot of new research showing how some of these transformer architectures are better in robustness. That's the latest research showing, and the other is also methods to improve robustness, such as using generative models. So we have a work where we show using diffusion models, because it has an inherent denoising nature, we can be very effective in handling all kinds of noises, right? Rather than just training on one kind of noise, which anyway takes away its natural accuracy. So I think there is nice developments, but yeah, still a lot of open challenges.
Cool. And we also have the last quick question about the generalization, because when you mentioned the neural operator, and it's very exciting to see how you leverage, for example, fast Fourier transform in those computation. But correct me if I'm wrong, but if we encounter a different shape or the domain with different boundaries, then the spectral domain are not necessarily the same. So so we wonder, how does your method train on, for example, one shape? How can they generalize to a different shape?
That's a very good question. We're soon putting out a paper on that. So the idea, we can learn deformable basis. We can look at the topology, do a decomposition. So lots of tools from geometry, right? We can bring in, and then we can do processing after, right? We have had the right basis. So, and also we can do Fourier continuation for the boundaries. For irregular boundaries. So I think there are a lot of good principles we can bring in.
Thank you for this answer. And yeah, based on time constraint, we should let you leave, but thank you for joining us today.
Thank you for organizing this. And I also love the graphic design, by the way. I'm a fan of all the posters when I went to the website. So thanks for putting this together.
Glad to hear that you like it. Thank you.
Have a lovely day.
You too. So now we will proceed to some questions for our opener, Yun-Chun. So the first question is that you pitched the application for this work in robotics. And we are just wondering how your method is robust to, for example, occluded or incomplete data due to some, scanning technology.
So I tried if we only have one viewpoint cloud, and the current method didn't work at all. But we're sort of robust to noisy point clouds, but there are still some improvements, some room for us to deal with one view or few viewpoint clouds.
Oh, that's cool. Then perhaps it's another opportunity for like future CVPR papers. Yeah, and the second question is also related to this context of like robotics. So basically, we can see like the kind of this is like a very important step to figure out, like for example, rigid transformation to mating two pieces of geometry together. But we wonder like what's your opinion on kind of extending this to, for example, predicting the entire path of how should we move one piece to mate with another piece, so that, for example, if we use a robotic arm to mate the two pieces together, we will be like collision free of like other pieces in this thing.
Yeah, I think we have to break down the process into multiple stages. So definitely the first one will be like grasp pose prediction. And we probably don't want the robot to grasp the region that will become the interface, right? And when we predict the grasp, then what we can do is we also predict what the final grasp pose will be, or final object pose will be. Because if we know the final object pose, we will definitely know how the final grouper pose will be, because this is like locally attached to the object, right? And then we have the start pose and the end pose. What we can do is run an existing motion planning method, like RT planner, so that we're able to plan a trajectory to execute it. Even though there are some other physical constraints, but like at the high level idea, we will do some like pose prediction and then run some existing motion planner to achieve this stuff.
That's good to know that there's already existing technology to resolve this problem. Okay, and another question is more related to the technical details of this paper. So correct me if I'm wrong, because you mentioned that you're using transformer to process pairwise point features after going through some some point net architecture, right? But we wonder, what is your intuition behind processing all pairwise information between 2 points, comparing to, for example, only processing like the pairwise information of the local neighborhood of a point?
I think there's the core reason that we use transformer is because the pose prediction task here is not predicting the pose of the input. It's not independently predicting pose for the input, but we have to depend on the other, the pose of the other shape. This is one intuition, and the second thing is we want to do this sort of like pairwise feature correlation thing inside transformer, is because we want to see if the model can inherently figure out like maybe like this patch on this point cloud and the other patch on the other point cloud, their local geometry are similar, or like the curvature are matched, something like that. So we didn't really, so this was our intuition. And I think one drawback was that because we didn't operate on the mesh level, if we have mesh level as input, then we definitely can do some heuristics to figure this out. But in the point cloud level, and we also don't have normals, so everything you have to need like large scale data sets, so the model will have to implicitly figure out how to mesh them together. That was our intuition, and also transformer has been shown successful in many tasks. So yeah, borrowing their strengths to solve our problem.
So that's really great. Just as clarification on this, so you say if your input is like a triangle mesh, for example, then do you think that it's possible to only process like, for example, local neighborhood information, or you think like the task? I think if we talk about input as meshes, there have been a couple of works even before deep learning era that have been shown successful, but there's a large gap between using meshes and using point clouds. Oh, yeah, that's really great to know, and also like show the power of using meshes. So another question is about like, are there some shape pairs that are just simply unmatchable with each other? For example, like a sphere and a cube. Are these kind of edge cases easily handled with your method, or?
Right. So I think this is the assumption that we made. We assume that these two parts are like can be assembled, and after assembly they will become a single object. That is our assumption. So if we broke this assumption, then definitely our model wouldn't have the ability to tackle it.
But I believe it will still be interesting to see how this model will how they will match like two unmatchable shapes together.
Yeah, I think this is an interesting test case.
Yeah. And then the last question is about like your work takes a point cloud as an input instead of the mesh, as you mentioned earlier. So would you using like a mesh reconstruction algorithm to actually evaluate the fit of the test time to like kind of do you think like using mesh reconstruction algorithm to evaluate the fit will kind of improve the performance?
I think we can definitely do this kind of trick, right? But I think we haven't done that one was because at the time I didn't figure out a way to backpropagate loss on the mesh level. So that's why we do it fully on the point cloud level.
I see, but yeah, perhaps today people will have more technology because we have more and more like differentiable like meshing algorithm, then that could be useful for this task. Cool. And yeah, I think that's all for the question for today. So now thank you everyone for joining this colloquium, and let's also thank our speakers again. And in addition to that, I also want to thank our artist, Tiffany Dang, for making the poster for this week, and I'll see you all next week.